CCI, Crash Course Instrumentation, presents Episode number 68, KCL in the Field, Neutral Balance, Hidden Branches, Meter Mysteries. Cold Open. In the field, a single node can explain a tripped breaker, a noisy instrument, or a melted neutral. Today we read 3 real-world nodes and let KCL settle the argument. Incoming equals outgoing. Viewer promise. By the end, you will use KCL language to diagnose neutral imbalance, spot hidden branches that steal current, and fix impossible meter readings by choosing the right conductors. Quick bridge from episode 67. At a split, rank the ease of each branch and expect the easier branch to take more. In the field, we care about where the currents meet and how many paths are actually touching the node. Section 1. Neutral balance in a 3-wire system. Picture a service with 2 hot conductors and a shared neutral feeding 2 branch loads. The neutral is the node where branch returns meet. When the 2 branch currents are equal in opposite directions, the neutral current shrinks. When the branches are uneven, the neutral carries the difference. Field test. Clamp only the neutral conductor. If your clamp shows more than expected, one branch is heavier, or a third path is sneaking current onto that node. Safety cue. Confirm the neutral bond location and use a clamp on one conductor only. Clamping hot and neutral together cancels the reading. Section 2. The hidden branch that stole current. Story setup. A control panel shows a mystery drawer that does not match the 2 visible loads. Node focus. The plus bus where both device feeds land. Inspection. A small diagnostic module is tapped at the same node on the backside of a terminal strip. It is your 3rd branch. Proof. Clamp the wire to each device one at a time. Add the 2 visible outgoing currents and compare to the incoming feeder. They do not match until you clamp the hidden tap. Plain English conclusion. At that node, incoming must equal the sum of outgoing. If it does not, you missed a branch. Section 3. Meter mystery. Negative current. Story setup. You insert a DMM in series and it reads a negative current. Node view. Your arrow guess was opposite the real flow at the node. KCL still holds. The sign only tells you the branch direction. Fix. Keep your original arrows. Say the words incoming or outgoing based on how the branch meets the node, then flip the probes or swap the meter leads if you need a positive display. Section 4. Mini-lab. Read 3 field nodes on the bench. Build 3 quick demos. A 3-wire neutral board with 2 adjustable loads, a panel mock-up with a hidden 3rd tap, and a series branch where you can flip meter orientation. Clamp the neutral only and compare to each branch current. Speak the node story. Incoming equals outgoing. Move to the hidden tap mock-up. Measure each visible branch, sum them, then find the missing branch by clamping every wire that touches the node. Insert the DMM in series with a branch backward to show a negative sign. Keep your arrows and your words consistent. Section 5. Common field mistakes. Mistake. Clamping both go and return in the same jaw. Fix. Clamp a single conductor. Mistake. Tracing insulation color instead of the node. Fix. Follow the actual conductors that meet at the node. Mistake. Comparing currents measured at different nodes. Fix. Pick one node and measure every branch touching it. Mistake. Forgetting parallel grounds or shields bonded in one place. Fix. Map all bonds so you do not miss a return path. Section 6. Field checklist you can use today. Choose one node. Mark arrows for every branch touching that node. Clamp or insert your meter on one conductor at a time. Say incoming or outgoing for each branch. Confirm incoming equals outgoing. If not, find the missing branch or a bond you overlooked. Tiny historical note. Telegraph maintainers chased phantom currents caused by stray bonds and ground returns. Their fix was the same as ours. Choose one junction, list every path, and prove the totals equal. Series wrap and tease. KCL and KVL are two sides of the same story: node totals balance and loop totals balance. Next series, we apply both to real troubleshooting case studies. Call to action. If this helped you think like a field tech, please like and subscribe so more students and techs can find it. Credits, on screen and spoken. Thank you to Tony Koopalt and the open source community for the Modiel materials that make Crash Course Instrumentation possible.